So I have here a Newton's cradle. And you've probably seen before, if you lift one up, one kicks out the other side. If you lift two up, it has twice the potential energy, transfers to kinetic, two kick out the other side. But here's the dilemma. Why don't we ever see lifting two up and swings down and then one kicks out the other side but goes twice as fast and then twice as high? Why don't we ever see that? It doesn't matter how many times I do it, I'm always going to see two kick out the other side. That dilemma is really the heart of today's lesson. What factors affect kinetic energy? So here I've got the marble launcher and a couple photo gates set up, and when I pull that down, thank goodness for slow motion, it goes up about 1/3 of a brick. So I was trying to hit 1 meter a second, and I came really pretty close to that. We'll try to get 2 meters a second. Pull it down, we let go, and we get more than one brick, kind of between a brick and 1/3. And we're a little bit shy 2 meters a second, but we'll keep that. And then we'll try to hit 3 meters a second. And 2 2/3 bricks for the height, and we're really close to 3 meters a second. And you can see that when we were doubling the velocity, it does not double the energy we get at the end. If we look closely at it, we'll see that when you double the velocity, it's pretty close to 4 times the kinetic energy. 4 times 1/3 would be 1 1/3, and we were pretty close to that, a little under, but close. Tripling the velocity would give you 9 times the kinetic energy. 9 times 1/3 would be about 3 bricks, and we're at 2 2/3. So it dissipated. I'm pretty comfortable that that's the pattern this is showing us. So we can now look at our formula for kinetic energy. We already know that the mass is involved, and if you double the mass, it probably does double the kinetic energy. We talked about that earlier. But now we know the velocity is squared. So our formula for kinetic energy is 1/2 times the mass times the velocity squared. Now if you understand those ideas, you should be able to do this ranking. So I'm going to give you a little bit of a quiz here. 4 different vehicles. This one is the smallest, 1,000 kilograms, going a certain velocity. This one's double in size, so double in mass, going the same velocity. This one is the smaller size, so smaller mass, twice as fast, bigger mass, twice as fast. Rank them in order from which one would have the most kinetic energy down to which one would have the least. So go ahead and pause the video. Okay, hopefully you have your predictions. Let's think about this in terms of pain. If this is a pain factor of 1, then a car going the same speed but twice as much mass would have a pain factor of 2, be twice as bad. Now we come over here and say this one is the same as the small one, but it's going twice as fast, and because you square the velocity, that actually has a pain factor of 4. And this one is the same mass as this, but it's going twice as fast, so it'll be 4 times as much as that one is, which gives it a pain factor of 8. So really the order is just reverse: D, C, B, and then A. Now this idea of going twice as fast giving you 4 times the energy is actually really important when you think about car accidents. If you are speeding, it definitely increases your kinetic energy, but if you happen to be going twice the speed limit, think about what that means in terms of physics. You'd have this much kinetic energy if you're going the speed limit. Same car going twice the speed limit, you have 4 times as much kinetic energy when you're going twice as fast. That means that if you get in an accident, the accident will be roughly 4 times as bad because you have 4 times as much energy that you have to dissipate. And usually that happens by the car rolling or slamming into something, which is not good news for the people inside it. So we learned quite a bit about kinetic energy today, and the main thing that we've learned is that the velocity affects the kinetic energy more than the mass does. So let's get back now to our dilemma. If we take 2 marbles and lift them up, now they have twice the potential. Why don't we see only one kicking out the other side but twice as fast? Well, the problem is because of the kinetic energy formula. And if you look up here at my numbers, you'll see that. When you put in twice the mass for lifting 2 marbles up on the first side, you end up with 1 unit of energy. But then if 1 kicks out twice as fast, this becomes a 1 for the mass, but the velocity becomes a 2. And when you square 2, you get 4. So we end up with now 2 units of energy at the end. So we end up with twice the energy that we would have started with if that was allowed. And that's against the law of conservation of energy. You can't get out more energy than you put in, so nature says, no, that's never going to happen. You'll always get out the same energy in the end that you put in the beginning. So that's why when we lift up 2, we always see 2 kick out again, because the conservation of energy doesn't allow 1 to kick out twice as fast. So there you have it. Kinetic energy in a nutshell. I'm just going to keep playing with this. Thanks for watching.